Greetings of the day, dear students. In this class, we are going to discuss about the ideal transformer. We will discuss its diagram, circuit diagram, and the waveforms of voltage waveform and induced EMF waveform, and the magnetizing current waveform, and also we will see its phasor diagram, and we will discuss one small example to understand its basics. Right? Yeah. Now coming to the ideal transformer. If it is an ideal transformer, its winding resistance, magnetic leakage, and iron losses are neglected. I repeat again: winding resistance, magnetic leakage, and iron losses are neglected. So, for example, that windings, which is nothing but a wire wound, a conducting material wound in the form of some coil, right? So obviously, as it is a conducting material, it will have some resistance, right? That winding resistance is neglected, and also the entire flux which is established, right, in the primary side is going to link the secondary side winding also. There won't be any leakage of flux into the air or surroundings, and also the iron losses are neglected. And one more important thing is, it is assumed to have infinite permeability. For example, the wire is wound on a core, or the windings, primary winding and secondary windings are wound on a core. Depending upon the material used, it will have its own permeability. So how do you understand that? Infinite permeability means, if the permeability is very high, then for small amount of current itself we can get more flux. Or in the another way, to produce the same amount of flux, if the permeability is high, that can happen with small amount of current. That is possible with small amount of current, right? So here we will assume it is going to have infinite permeability and zero reluctance. Of course, the topic itself indicates ideal transformer. It is impossible to realize such a transformer practically. Right? So if you look into the diagram, primary side applied voltage V1, primary side turns N1, and because of this applied voltage, some current I1 will be flowing in the winding. Because of this current flowing in this winding, some flux phi will be established, right? And some EMF will be induced in the primary winding, that is denoted with letter E1. EMF induced in the primary winding, E1. Now whatever flux that is established in the primary winding, right, that is also going to link the secondary winding, right? Because of this, what happens is, some EMF E2 will be induced in the secondary winding, E2 EMF induced in the secondary winding, which is having of turns N2. Now the voltage available across the load terminals or secondary side is some V2, right? Yeah. Now if you observe, even though there is no load is connected across the transformer, it is going to draw some small amount of current. Very important, dear students. Even though there is no load is connected across the secondary, some small amount of current will be drawn, right? That current, no load current, it draws some current. That is the magnetizing current. Magnetizing current denoted with letter I mu, right? And also this current is going to lag the applied voltage by some angle 90 degrees, right? Now this magnetizing current and the flux both will be in phase. This is what we have drawn in this phasor diagram. Im and phi both are in phase. And one more important point, the voltage induced EMF E1 at every time will be equal and opposite to the applied voltage V1. So here it will be exactly 180 degrees out of phase with respect to the V1. That is the reason why here V1 is drawn in this side, and it's quite opposite. E1 is drawn 180 degrees out of phase. If you observe the waveform also, observe this V1 is starting here at origin, and E2, this dotted line indicates the E1. This dotted line indicates the E1. Now the current I mu, this current is lagging the voltage by 90 degrees. This angle is 90 degrees. So here this is some small amount of current is going to flow, I mu. So these three waveforms are very important with respect to the ideal transformer. So this is the phasor diagram for ideal transformer. So circuit diagram, and these are the waveforms. The key points are E1 and V1 will be out of phase by 180 degrees, right? Yeah. Now this current lags, magnetizing current lags applied voltage V1 by 90 degrees. Flux and Im will be both will be in phase. These are the key points, right? Now let me see a small example. And one more important point, whatever the current drawn I0 can be resolved into two components. It is resolved, for example, observe dear students, during no load I told you that some small amount of current will be drawn. That I0 can be resolved into two components. This I0 will be at an angle phi 0 with respect to the V1. This is what I have indicated here. This I0, for example, if this is a small amount of current I0 flowing, this I0 will be at some angle with respect to the applied voltage V1 and phi 0. Now this I0 can be resolved into two components. One is the horizontal component and another one is the vertical component, right? One is the horizontal component and another one is the vertical component. So horizontal component denoted with Im, called as magnetizing component. Very important. I0 is resolved into two components. Im is the magnetizing component and the vertical component Iw is the working component, right? Now this Im is also equal to I0 times sine phi 0, and this Iw is equal to I0 times cos phi 0. Clear? Don't think that if you write angle here, the entire analysis goes wrong. If you have drawn I0 correctly only, and you have indicated V1 also correctly only, but instead of that is the angle between this voltage and current. If unfortunately you have indicated that angle here, then this Im and Iw will get in a wrong manner. This is wrong. Here this is the angle phi 0. Now this angle will be 90 minus phi 0. 90 minus phi 0. That is the reason this horizontal component you got sine term, because the angle is here. Similarly for working component you are getting cos term. Observe. So please don't commit mistake. There is a possibility or chance to commit the mistake. This is the key point, right? I repeat again, I0, that is the angle between I0 and V1 phi 0, right? Yeah. So here from the problem, from the data given, I repeat again, a voltage notation something given like this 2400/400, it is to be understood as primary voltage is 2400. Primary voltage V1 equal to 2400 and the secondary voltage V2 equal to 400 volt. The transformer is single phase transformer and it takes a no load current of 0.5 amps. No load current I0 equal to 0.5. The core losses are given. The core loss is 400 watts. Determine the values of magnetizing and working component. I repeat again, it is simply nothing but resolving the I0 into horizontal and vertical components. So once you know phi 0, the angle, then easily we can find out the magnetizing component and working component. How we can find out the angle phi 0? From the given losses, the loss is given, 400 watts loss is given. That losses will be equal to V1 I0 cos phi 0. This is the in this entire problem, this is the key point. If this concept is missed, then we cannot go further. The losses, the losses are given. V1 I naught cos phi naught equal to 400 watt. V1 I naught cos phi naught equal to 400 watt, right? Yeah. Now already we know V1 and we know I naught. From this we can find out cos phi naught equal to 400 divided by V1 I naught. So cos phi naught is 0.33. What will be the phi naught? Cos inverse of 0.33. The angle is 70.52 degrees. So this angle we got this angle is 70.52 degrees. Now we want IM and IW. IM equal to I naught sin phi naught equal to 0.5 sin 70.52, 0.471, right? IW equal to I naught cos phi naught equal to 0.5 cos 70.52, 0.166 amps. Observe, this is drawn in the form of a diagram, phasor diagram, and draw the phasor diagram, right? So here, as we have discussed, IM and phi will be in phase. That is what we have drawn here. IM and phi are in phase. V1 and I naught will be at an angle phi naught. That is what we have drawn here. That angle is around 70.52 degrees. I naught magnitude 0.5 amps. And the horizontal component IM equal to 0.471. Vertical component IW equal to 0.166. And 180 degrees out of phase with respect to the V1. E2 is 400 volt, right? So this is how we can solve the this problem. Clear? So dear students, I repeat again, if this concept is given, okay, the assumptions are important. 3 assumptions are made: winding resistance, magnetical leakage, and iron losses are neglected, and also it is going to have the infinite permeability and zero reluctance. And while attempting this question in exam, this diagram, this waveforms and this phasor diagram gives you good impression and it will help you to score more marks, right? So, and after that, one more important point is phi naught is the angle between V1 and I naught. V1 and I naught. Okay. Okay. Thank you.